we will start looking at logistic regression now. And the plan for this involves introducing logistic regression, deriving map and MLE in the opposite order. And then I want to revisit this connection to loss minimization. What we have seen so far is we've seen linear models. We've seen the idea of learning as loss minimization. We've seen these Bayesian criteria for learning. Turns out logistic regression nicely combines all of these ideas, in particular linear classifiers with these things. We'll see what logistic regression is. I'll talk about training a logistic regression classifier, but then cleverly, I won't tell you anything about how to actually train it. I'll go as far as deriving an object or showing the objective function. And in your homework, you're going to take the gradients and derive the stochastic gradient descent for that objective and implement it. And there's a nice connection to loss minimization, which we'll come back to. Most likely, we won't have time for that today, but we'll come back to that at the end of this unit. Let's look at logistic regression. Despite the name saying regression, we are working on the task of binary classification. The input is, whereas it's the same thing that we had for perceptron and SVM and all those cases. We have features which are d-dimensional vectors. I'll call them X. And our labels are +1 or -1. We assume that we are given a training set consisting of labeled examples. So we are still operating in the supervised setting. So the X is a vector and the Y is a -1 or a 1. The output Y is discrete. But for logistic regression, instead of predicting the label directly, let's predict the probability that the label is 1 given an example. I can do that, right? I can try to construct a probability distribution for every example, the probability that the label is a 1 given the example. Importantly, that means our output space is not going to be -1 or 1. Our output space is going to be a probability. Probability is a number between 0 and 1. So our hypothesis space now will contain functions whose output is in the range 0 to 1. And that number is going to be interpreted as the probability that the label is 1 given the input example. Effectively, if we have to predict a number between 0 and 1, that means we are essentially we have a regression problem because we need to predict a real number in this range, right? So we're back to the question of, can I invent a hypothesis space that allows for this thing, that takes a vector as input and produces a probability, a number between 0 and 1, which we are going to interpret as the probability of the label given the example. Of course, there are many such functions possible. There are many functions that can take a vector and produce a number between 0 and 1. In particular, what logistic regression does is it uses this particular hypothesis space. It assumes that there is a certain weight vector, W. That weight vector is used by first taking the dot product of the weight vector with the features, so W transpose X, and then applying this transformation here called the sigmoid transformation. The sigmoid transformation is simply 1 over 1 plus e power minus W transpose X. So the sigmoid, I can write it independently of this. Sigmoid of Z is nothing but 1 over 1 plus e power minus Z. So the hypothesis space for a logistic regression is nothing but a linear function with a sigmoid transformation. Sometimes it's also called the logistic function. There are many, many sigmoid functions that exist. When people say the sigmoid, they usually mean this. this particular function here. 1 over 1 plus e power minus z seems like an arbitrary collection of symbols. Why did you pick that? Why not anything else that you could? There are many, many ways of taking a number between the W transpose X is a number, right? There are many ways of taking a number and squashing it into this range between 0 and 1. What makes this better than other things? Turns out this is a very reasonable choice. We'll see some hints about why later. Yes. No, we are interpreting this h of x as the probability of plus 1 given x, or probability that the y equals plus 1 given x. Why this function? As we will see later. And I'm not going to go into too much detail about why. There are historical reasons why this works. There are practical reasons why this works. If you really, really want to trace the history of this class of functions back, you will end up very quickly in statistical physics from the 1920s. And that's a different class. Um, I'll give you some hints about why later. And for our purposes, it works nicely because it has some nice properties. But before we do anything, let's look at this particular sigmoid function. 1 over 1 plus e power minus z. What is its domain and range? What can the z be? Can z be infinite? What's Why do two people say no? Why?
Certain set like input that's like finite and our weights.
Well, I mean, this is forget about inputs and all that. This function, we are just examining this function inside the box and seeing what it behaves like. So can this function take infinity as an input? Yes. Can it take negative infinity as an input? Can it take any real number as an input? Yes. What is its range? 0 to 1. In fact, it looks like this. No, this should be sigmoid. So it's a S-shaped curve. It squashes the function, and for all practical purposes, when z is really small, it's practically 0. When z is really large, practically 1. And it tends to 1. When z is infinite, it's equal to 1. When z is 0, negative infinity, it's equal to 0. And in practice, when z is more than 10 or something, it's so close to 1 that it might as well be set to 1. When z is less than minus 10, it might as well be set to 0. What's the derivative of this function with respect to z? You can work out the details. I'm not going to go into this. I'm sure you know how to take derivatives. But one of the cool things is the derivative of the function is simply sigmoid times 1 minus sigmoid. I don't know why. That makes me happy. There's a few interesting things there. If we are interpreting the sigmoid as the probability of the label being 1, then what's the probability of the label being minus 1?
1 minus that.
Exactly. So the derivative is simply the probability that it's 1 times the probability that it is minus 1, which is kind of cool. Once again, it's trivia. It has nothing. It's just a neat property. Going back to logistic regression. According to logistic regression, we are going to assume this model that the probability that the label is 1 is the sigmoid applied to the linear transformation of the features, which means the probability that the label is 0 is 1 minus the sigmoid, which is simply e power minus w transpose x divided by 1 plus e power minus w transpose x. If you don't trust me, you can take 1 minus this quantity here, you'll get this thing here. Let me clean this up a little bit. The second expression, this thing here, right? I can multiply both the numerator and the denominator by e power plus w transpose x. When I multiply the numerator with e power plus w transpose x, this quantity and this quantity multiply together to give me 1 divided by e power w transpose x plus 1. So let's reorganize these things. I'm going to write it in the same. I can rewrite it as 1 plus. So the probability that of predicting 1 is 1 over 1 plus e power minus w transpose x. The probability of predicting minus 1 is 1 over 1 plus e power plus w transpose x. Right? So when I want to predict the label plus 1, I multiply this thing by minus 1. When I want to predict minus 1, I multiply a plus 1 there. So the probability of predicting any label y given x, assuming that the parameters are w, is 1 over 1 plus e power minus y w transpose x. Do you see that? We're back to y w transpose x. The same quantity shows up again, which is neat. I don't know why, but that also makes me happy. It means that it's easier to teach the class. Any questions? Just a quick side note here. In this model, in this approach for defining a binary classifier, I have directly just jumped in and said, let's assume that the probability of y equals plus 1 given x is the sigmoid. I didn't tell you why. I mean, I just said, just trust me, this is what's done. I could have done things slightly differently. Instead of this, I could have said, I have probability of y given w or given x, right? I can apply the Bayes rule here. This is nothing but probability of x given y times probability of y divided by probability of x. My prediction will be the label y that maximizes the probability. So max over y, which is nothing but, or argmax. I could have done this. I'm not saying I'm doing this, but I could have done this. Importantly, I am using the parameters of my model directly to define this probability function, instead of using the parameters to define these two other probability functions. Right? Yes. Because I'm maximizing over y here, and the denominator does not contain any y term, so it doesn't matter. So think about what role your parameters play in this process. On the left-hand side, let's call this logistic regression. On the logistic regression side, the parameters of the model, they're being put to work to describe this function here, p of y given x. On the right-hand side, if I had parameters, I would be using them to describe two different functions. This term here is the likelihood term. This term here is the prior. This is directly the posterior. I could be using the parameters directly to define the posterior, or I could be using the parameters to describe the likelihood separately and the prior separately, and then use Bayes' rule to construct a decision rule to predict a label. I could have chosen two different ways of building models. I described this approach where we directly model the posterior. This kind of a model is called a discriminative model, where the model parameters are directly used to describe the label output probability given inputs. This kind of a model is called a generative model. Unfortunately, in this semester, I'm not going to be spending any time on generative models, but there's a very rich literature on generative models. Generative models include things like, you may have heard of hidden Markov models is a generative model. Topic models, which used to be a very big deal around 2001, are an instance of a generative model. You may have heard of something called a naive Bayes classifier. Have people heard of naive Bayes? So a naive Bayes model is a generative model. It turns out logistic regression and naive Bayes have a very close connection to each other. But unfortunately, because this semester is only so long and not double its length, we're not going to get into the details of this. But it's just worth knowing or noticing that we are using the parameters of the model to model P of y given x directly instead of P of x given y and P of y. Okay? Okay, so let's say that I've trained this model. I now have this expression here. How do I make a prediction? I already told you the answer, but can you concretize that? How do you, oh, there's a question. Can I explain the difference between the generative and discriminative models again? So a generative model is something that where we explicitly model two different probability distributions. We explicitly model P of x given y, probability of the input given the label, and the probability of the label, and then use Bayes' rule to construct this expression here. And if I need to generate a label, I will take the label that maximizes the product of the likelihood and the prior. So my model parameters, some parameters are dedicated for the likelihood term, some parameters are dedicated to the prior term. In a discriminative model, we use the model parameters to directly model the probability of the label taking a certain value. We don't care about the story of how the example was generated, given the label, P of x given y, or the prior probability. We just care about the output probability of the probability of the output. In this case, the output is the label given the input. So the difference is, are we directly modeling the probability of the label given the input, or are we inverting the problem and modeling these two expressions separately? I also realized just now that this term here, generative model, predates the modern use of generative AI. Generative AI is a different beast. It just so happens that all the generative AI models internally, they actually use discriminative models. Discriminative models tend to be far more successful if you care about predicting certain labels, which is, it's a little bit of the word generative has taken on new meanings in the last maybe 5 years. I hope that's clear. So how do we make a prediction? When a new example comes in, we have P of y given x, and we have two labels, either -1 or +1. I can ask, is the probability of -1 more than the probability of +1? Right? So if probability of -1 given x is greater than probability of +1 given x, then I predict -1. And otherwise, you predict +1. Let's focus on the plus side. So probability of -1 is less than the probability of +1, then you predict +1. But the probability of the label being -1 is nothing but 1 minus the probability of the label being +1. Which means, let's put a greater than equal to here, less than equal to. So I have probability of +1 on both sides. I can move this quantity to this side, which is nothing but multiplying this by 2. I get rid of this. And I still have a 1 here, so let's bring that back. And now I can bring the 2 down. That's is the probability of +1 is more than half, then you predict +1. The probability of -1 is more than half, then you predict -1. Seems intuitive. So if you compute the probability of +1 given x and your current parameters, if it's more than half, then you predict the label is +1. Otherwise, of course, the probability of -1 is going to be more than half. You predict the label is -1. But if your probability itself was defined using this expression, what is this decision, P of y equals +1 given x is greater than equal to half? What does that correspond to in terms of the W transpose X? Can someone take a guess without actually doing the math? What was the decision rule that we used for perceptron? +1 if what?
Negative y W transpose x is less than 0.
We don't have a y yet. We need to predict. How do you make a prediction with a perceptron or SVM in your homeworks? There's no mistake. You're given a new example. You don't know if there's a mistake. You look at the W transpose X and you look at its sign. What does sign mean? Sign is the same as saying if W transpose X is greater than equal to 0, then you predict +1. Otherwise, you predict -1. Let's see what happens with this probability here. 1 over, this probability is nothing but 1 over 1 plus e power minus W transpose X is greater than equal to half. That's nothing but, I'm going to continue here, 1 plus e power minus W transpose X is less than equal to 2. I'm just inverting both sides. I can get rid of a 1 there. So you have e power minus W transpose X is less than equal to 1. I can take log on both sides. Minus W transpose X is less than equal to 0. Or W transpose X is greater than equal to 0. Predicting that the label is a 1 when the probability of +1 is greater than equal to half is exactly the same as taking the sign of W transpose X. Another reason why this is a good function. We have the same decision rule. We just have a probabilistic interpretation for this decision rule. So prediction is the same. In fact, we are operating on the same hypothesis space as far as the decision function is concerned. It's a linear classifier. Logistic regression is a linear classifier that just additionally also predicts the probability and is trained by assuming this probabilistic model. Questions? I didn't say anything about performance yet. I only said they are the same hypothesis space. It turns out, empirically, and you might find this in your homework and maybe your project, logistic regression, SVM, and average perceptron tend to perform generally similarly, provided you do your hyperparameter tuning, the best hyperparameters for each of them independently. Each of them, when they are tuned appropriately, will perform roughly equivalent. Average perceptron, not just perceptron. But they don't need to, right? I mean, just because I'm using this hypothesis space does not mean that my learning algorithm is going to work well on finding the right hypothesis. Speaking of learning, let's look at training a logistic regression classifier. First, we'll look at maximum likelihood estimation, and then we'll add a prior, and then look at go to maximum a posteriori estimation. We're training a binary classifier, so we need to operate in the same setting that we've had for all binary classifiers. We have a data set, x comma y. X is a vector, y is -1 or 1, and we have m such examples. Our goal is to find a weight vector because the hypothesis corresponds to the weight vector. Our goal is to find a weight vector such that the probability maximum, we maximize the likelihood of the data. The likelihood of the data, if the data is S, the likelihood of the data is probability of S given W, and we want to maximize the likelihood of the data. As always, we assume that our examples are drawn IID. What do we do next? How do we define the likelihood? What does the IID help? How does the IID help in defining the likelihood term? This S consists of x1, y1, x2, y2, all the way to xm, ym. When I say probability of S given W, I'm essentially asking for probability of x1, y1 given W. I know that this pair is independent of this pair, and so on. How does that information help me to make this probability clean it up? How does it help me clean it up? Someone who's not answered. Yes, you've not answered.
Yeah, take the product of all the probabilities of y, like yi given xi and w.
Technically, it's not yi given xi and w. Technically, all we know is it's this is because it's IID. I'm writing from the bottom up here because I didn't plan this out. It's simply xi comma yi given w. That's all we have, because all we know is the example xi and yi is independent of all the other examples. And that's true for all I. But then how do we proceed? The same thing that we did for the previous thing. So I know that probability of xi of S given W is the product but I can write this as probability as a product of probability of xi given W times I can do that, right? But the weight vector does not dictate where an example is situated in this instance space. The target function does not dictate the choice of the example, which means the first term here is independent of W. This is nothing but the product now. What we are going to do is maximize, I want to maximize over all possible W's. The first term, P of xi, does not involve a W at all. So this is exactly the same as taking the argmax over all the W's of just the product of the second term. And that's convenient because our logistic regression tells us exactly this expression there. So the likelihood term can be written as simply the product of P of y given x comma w. And then we do the usual trick. We don't work with likelihoods, we work with log likelihoods. And one point here to note is we cannot assume a normal distribution because we've already assumed a different distribution. P of y given x comes from the sigmoid. So we're going to work with the log likelihood here. And taking the log means that the product becomes the sum. So we are left with, we need to find the maximum of the sum of the log probabilities of the label given the features. We assume, by definition, we assume that the probability is the sigmoid of the linear transformation. And log of that is simply log of this, the probability is simply log of this expression here, which is negative log 1 plus e power minus w transpose x. I just took the log of that sigmoid there. So I can plug this quantity here instead of what I've written there. So equivalently, we are solving maximizing over all weights, the sum over the negative log of 1 plus e power minus w transpose x. Maximizing a negative quantity is the same as minimizing the positive quantity. So I can get rid of the minus and replace the max with the min. Let's start with, let's see what we had here. Our goal was to solve maximum likelihood training of a certain discriminative probabilistic classifier that assumes that the posterior probability of the label given the input features follows this logistic this particular logistic model. That's a very complicated way of saying the probability of the label given the example. We assume that the probability of the label given the example is the sigmoid function applied to the linear transformation. Our goal is maximum likelihood training in that setting. And what we end up with is we are minimizing this quantity here. Minimizing the sum over log of 1 plus e power minus yw transpose x, which turns out this expression here, this is our first introduction to a new loss function. We had the hinge loss for the SVM, right? Just like that, this thing here is called the logistic loss. Unfortunately, it does not have a fancy name like hinge loss for support vector machine. It's a more direct logistic regression uses the logistic loss. We are minimizing the logistic loss. We are training a linear classifier by minimizing the logistic loss. Training a linear classifier by minimizing the logistic loss ends up being equivalent to performing maximum likelihood estimation of this discriminative probabilistic classifier that assumes a logistic model for the posterior distribution of the label given the example. Yes.
Why did the argmax change to a max and then subsequently a min when in the what is it, the maximum likelihood estimation we did for least squares regression, it was still just argmax and argmin?
Yeah, so argmax is simply the weights that maximize this quantity. Min is simply the value that is minimized. So they are solving the same problem. Min is the minimum value of this. Argmin is the weights that minimizes that quantity. And when I want to write equivalence, I can't say that this, if I written max there, I can't say the two maxes are equal. Because of what I did here. The two maxes cannot be equal because the left-hand side is this expression here, and the right-hand side is this expression here, and they are clearly not equal. But the W that maximizes the left-hand side and the right-hand side are equal. So the argmax are, I can put in, the reason I use an argmax is because I want to put an equal sign. It's just a technical detail. Other questions? I showed you maximum likelihood estimation. Let's look at an example of maximum a posteriori map estimation. For map estimation, I need to have a prior distribution of over the hypothesis space because I need to maximize this quantity. So I need to define P of H. The hypothesis space is entirely defined by the weight vector. So let's consider a specific prior. Let's assume that each weight in the weight vector is drawn randomly from the normal distribution centered at 0 with a certain standard deviation, sigma. So the probability of the weights is, because every weight is independent, I can write down the probability density here for the weights as being the product over each weight in the weight vector. And I've just plugged in the probability density function for the zero mean normal with a standard deviation sigma. That's your prior probability of the weight vector. Okay, this is an assumption. How do I know this is true? Don't ask me. I just made this assumption, and I'm not claiming this is true. I just want to see what happens if this were true. So now I can apply maximum a posteriori estimation for logistic regression with this particular prior. Remember, we already did map estimation. The goal of map estimation was to maximize the likelihood of the data, and we ended up with that expression there. The goal of, in particular, the goal of map estimation is to, the goal of maximum likelihood estimation was to maximize the likelihood, and we ended up with that expression. What's the goal of map estimation? It's to maximize the posterior probability of the data, of the hypothesis given the data, P of H given D, which is equivalent to maximizing the product of the likelihood and the prior. There's a question on Zoom. So why in maximum posteriori, why do we use this PDF, whereas in maximum likelihood, we don't? That's really a definitional difference. In maximum likelihood, we assume that the prior distribution is uniform. If the prior probability is uniform, that means, technically speaking, we are always doing P of D given H times P of H. But if this quantity is uniform, that means it's a constant. And in the problem where we are maximizing over all hypotheses, P of H does not feature because it does not change any values its value does not change across a choice of hypothesis. In maximum likelihood, we are essentially dropping that assumption that the prior probability is uniform, and we are bringing in other assumptions. We are assuming that the prior probability is something else. So technically speaking, in maximum likelihood, we also still have a prior distribution. We are just, because it's a constant, we can ignore it. Whereas in these other cases, because we are no longer assuming that P of H is entirely defined by W, so in this case, it's P of W. Because we no longer assume that P of W is independent of W, in particular, P of W is dependent on W, we can no longer get rid of that in this maximization problem. So we are in the full maximum a posteriori setting. We are assuming that the prior is Gaussian. That's right. So the goal is to maximize the product of the likelihood and the prior. So we are finding the most probable models given the data. And actually, we have all the pieces we need to work this through. We already did the likelihood term, right? We worked on the likelihood term right here. So and once again, I'm using argmax here. So for maximum likelihood map estimation, we're maximizing probability of the model given the data, which is the same as maximizing the probability of data given the model times the probability of the model. First thing, let's take log. Let's work in the log space to simplify things. So it's the sum of the log likelihood if we're maximizing over all the weights, the sum of the log likelihood and the log prior. The good news is we've already worked through the log likelihood term right there. So we don't need to, I'm not going to go through the same process again. I can just copy and paste it. And the log likelihood can be expanded out to be this term here. The log prior is the log of this expression, log of a product. This time it's over all the weights. There are d of them. Log of the product is simply the sum of the logs of some constant 1 over sigma, which doesn't depend on the weights, plus the log of e power minus w square by sigma square. Log of e power is nothing but the thing inside the exponent. So I can just write it as the sum over all the weights of w square divided by sigma square. Plus there are a whole bunch of constants which I'm not going to write. Constants with respect to the w. There are terms that don't depend on the w. So the goal here is to maximize this entire expression with respect to w, so the constants don't matter. I have maximized the sum of a negative here, so I can get rid of the negatives. So I can just minimize. Okay, I cleaned this out. And sum of w square is nothing but the dot product of w with itself. So I can write it as w transpose w times 1 over sigma square. I just moved it out. I've cleaned it up. You can trust me that this is correct. But don't trust me so much that you don't look at it again. Now I can move out the minuses and convert the max into a min. And now I have an expression that must look awfully familiar. I'm minimizing the sum over the logistic loss plus some constant 1 over sigma square times w transpose w. I'm rushing through this mostly because I want to get to the punchline, but I do want you to look at it once more. All I have done is just boring algebra. There's nothing particularly intellectual in what I did. It's just symbol manipulation. But there is something interesting here. Training a logistic regression classifier in the map setting is equivalent to solving this minimization problem. Where have you seen this before? Not exactly this minimization problem, but something like this. Yes. Well, forget the stochastic gradient descent. We've seen this with SVM. Stochastic gradient descent is just an algorithm for solving this part. But SVM has the sum of a regularizer and a loss mediated by some positive number. We have the exact same thing here. So that means you can actually write down stochastic gradient descent for this. You should do that as an exercise. And if the idea of doing it as an exercise doesn't motivate you, you should do it because it's the first question in your next homework. You can take the gradient of this term. It will look different from SVM, but not too different. Turns out there are other training algorithms that exist. There's something called, before SGD became like the de facto algorithm for training logistic regression, even in maybe even 15 years ago, the standard algorithm for solving this optimization problem was not stochastic gradient descent. It was an algorithm called LBFGS, which is short for Limited Memory Broyden Fletcher Goldfarb Shannon. I feel very proud that I can remember that. It's a class of optimizers that use something called, that belongs to the family of quasi-Newton methods. But it turns out today people just use gradient-based methods. Stochastic gradient descent is the standard thing. So quickly, wrapping it up, and then I want to, well, even before I wrap it up, this expression here is interesting. I have this regularizer. Basically, what the prior does is it manifests itself as a regularizer. The regularizer imposed preferences over the hypothesis space independent of any data. The prior imposes preferences over the hypothesis space independent of any before you see any training data. So it behaves, it has a similar sort of a flavor. So you should not be surprised that they end up being similar. This is the origin story for, this is the Bayesian origin story for the L2 regularizer, W transpose W. The margin-based origin story essentially said, minimizing this quantity maximizes the margin. We like larger margins because Vapnik said so. The Bayesian story says, minimizing this quantity essentially minimizes, by minimizing this quantity, you have assumed that the prior distribution for your weights is the normal distribution centered at 0 and all the weights are independent of each other. They both give you the same expression. Which of these is the right answer? Whatever makes you sleep better at night is the right answer. Because they are solving the exact same problem. This is just an interpretation of that solution. Just like with least mean squares, we have two different lenses to look at the same thing. And then there's a new loss here, which is fun. We have a new loss in our zoo. So logistic regression, to wrap up, is a classifier that predicts the probability of the label being -1. It turns out it's the discriminative counterpart of the naive Bayes classifier. We've not seen naive Bayes classifier. It's super easy, but very tedious, which is why I stopped teaching it. It's kind of, it's very easy to get lost in the tedium, but it's a very easy thing. I have slides if you want, you can go over it. It's a discriminative classifier that can be trained using the MAP criterion or the maximum likelihood estimation criterion. In either case, we minimize the logistic loss. In the maximum likelihood setting, we also get this extra regularizer term that is the same as the one that we saw for SVM. Okay, I'll wrap up here. On Thursday, we are going to just very briefly revisit loss minimization because I want to kind of put all of these things on the same page, and then we'll start neural networks. Get started on your homework. I think you have everything you need to do for the homework, except for the extra credit question. Start early because all your deadlines are going to pile up in the last week.